good morning or good evening, depending on where you're joining from. Our panel today is Net Zero, How to Get There. Even as other greenhouse gases and air pollutants affect the climate, the evidence is clear that carbon dioxide is the main driver of climate change, and stabilizing the climate will require reaching net zero CO2 emissions. That is a quote, or paraphrase in some way, from the most recent UN report on climate change. I'm joined here by a panel that the agenda will be each will give about a 4-minute or so personal view on the topic, and then we'll open the floor to Q&A. Allow me to introduce our panelists. We have Dr. Mike Cook, distinguished structural engineer, who's given us so many of our iconic shell and spatial and tensile structures. And he initiated the Engineers Declaration of Climate Emergency in the UK and leads the Institute of Structural Engineer Climate Emergency Task Group. Followed by Dr. David Collings. He's a technical director at Arcadis and a bridge engineer who's focusing on minimizing their carbon emissions. And we have Corentin Fivet, professor at EPFL, who focuses on sustainable building system, and he co-chairs one of the IASS's new working group 18 with Professor Olivier Baverel on life cycle design and assessment of spatial structures. So we'll start with Professor Cook. The floor is yours.
Thank you very much, Samar. And there's my first slide. I'm going to speak very quickly, and I want to give a very broad overview of how we will get to net zero, and to go into the full depth and the full extent of what really needs to change, because it's not minor. At least it's now recognized that we have a climate emergency. The latest data is showing very clearly that it's induced by us and our development and our use of fossil fuels. I'm going to do it in 3 diagrams. This first diagram is really about the reduction over time of our carbon emissions, and this reminds me to say how there are some early gains we can get in now and over the next few years as engineers to help restore equilibrium. Early gains, I don't know if you can read it, but as engineers alone on our projects, how we can decarbonize, change the materials we're using, be more effective and efficient. But if we work with our architects and change the definition of what we're trying to do, and if we work with our clients to actually really think what outcomes they want and how we can change the type of project that we need to give them, we can cut carbon more and more. So we have to go well beyond just the materials we use. But still, we have the rest of the problem. We have a bit more time to solve the rest of the problem, but that problem is a massive problem. We know that nature around us is already collapsing, the polar regions and so on, and we know there is no real technological magic bullet. They're not magic bullets. We've got some bullets, but they're no magic ones, and the costs are huge. We know that our prosperity that we kind of live for is driven by consumption development. So we have to change how we consume, how we develop. And we know money is the big valued thing that drives the economy. These are problems for us in terms of making major change. We don't really value enough future generations. We think we do, but we don't sacrifice enough for future generations. And the government takes the short-term view. My second diagram is about this, the tipping point, this need for massive change, and the red and moving to the green. We have to pull down the red. We've got to decline a lot and build up the new green. On the left, you've got these stimuli. It's important that we can see. Fortunately, unfortunately, the climate emergency is visible. The declining health, and COVID is a clue. Declining security through fires, through flood, and changes in weather patterns, in food insecurity, and social instability that's coming out of that. So we're seeing things which will drive change. Those drivers are not just technical changes, technical opportunities to do new things, to capture carbon, to create new materials. Social change, what people are demanding is changing, and what they'll buy and put their money towards. What risk means. Climate is now such a risk that investors are no longer wanting to invest in buildings, in infrastructure projects, constructions that could impact on climate change. businesses are starting to think differently about their overall values and how they change what they do. And even governments are declaring net zero, although a lot of that is really with great nervousness that it means they'll have to change the way the economy runs. So what can we do? We've got to face the facts. All engineers, especially who understand more complex systems, they need to think beyond their normal frame of reference into wider frames of reference. We've got the ability to do that. So as well as reducing carbon in our own practice, in our own research, we've got to seek ways to change the brief and raise the ambitions of the outcomes of any of our work. And more than anything, we've really got to think now about the future, about people and the planet. We've got to think differently. We've got to change our values as to what we really value and influence at every level. What we need is this paradigm shift. We need to make changes across the board. And the third diagram, therefore, is Kate Raworth's Donut. If you can get hold of, if you haven't read it, Donut Economics, it starts to reframe the world around us in a way that I think is very, very valuable. The green is the place we need to be on this diagram. It's the place where we're building a safe and just space for humanity. It means that we're not exceeding the ecological ceiling, where we harm the environment, harm the planet, but it means we are providing, we're not falling into the hole in the middle, which is falling short on the social provision that people have the right to. And that means we have to start thinking a lot more about the less well-developed world and their rights to a better life. And that means that some of our overconsumption in the so-called global north is starting, we have to start to compromise. And then, so really, what does this look like? Well, I think that you want, if you want to be optimistic, you could say that massive investment will be needed. We need to shift money toward new technologies. We need to think differently about how we educate people so they really understand a lot more than the narrow fields that we teach in now. How does the world work? We need industry to have new values and think about future generations. We need investment and capital to be put in places which will value future generations and value the planet. We have to limit what capital is allowed to do. We need to globally coordinate because this is a global issue. It's no good one country solving its notional problem. Boundaries, climate knows no boundaries. That's a tricky one. Prioritizing global health over minority wealth is a big hurdle for us to overcome. So I said I didn't want to underplay how difficult this is, but if you ask a question about how do we reach net zero, it isn't about tinkering at the edges. It's fundamental change. I'll just say it's got to be done. It's worth doing. Lives are better as a result. And I wanted to just point you to the Living Building Challenge, pulling back into a sort of real world. What do we do in the next few years? Look up Living Building Challenge, and it sets out some very good targets to achieve on projects in your research, wider, broader set of outcomes, which will be much more beneficial for the position. Thank you, Samar.
Thank you, Mike. David?
Hi there, David Collings. I'm a technical director at Arcadis. I've been measuring carbon now for about 20 years. I first published some data back in 2005. We had a bit of a lull in thinking about carbon through the 2007-8 financial crisis, but it's becoming a big issue now. And in terms of message, I think that from the research that I've done, the key message is that to get to net zero, we have to use less material. That is the big thing that we need to look at. And I've been measuring material. I've measured in infrastructure. I've measured in buildings. I've measured in bridges, and there are a number of points that come out from this research. And one of them is that big projects use a lot of carbon, and if we can reduce the number of big projects, it actually has a big effect on the carbon. In that, from the data, when I collect data, what we often find is that the largest few projects have almost 50% the carbon that's being used. The smaller projects, even though there are lots of them, don't add up to the amount of carbon in the larger projects. So reducing carbon in larger projects is one of the things we need to do. And if you saw my lecture on Monday, you will see that we have this issue for space structures, that the amount of material in the larger space structures was very significant compared with the smaller ones, that there was up to 4 times as much per square meter on some of these larger ones than for the smaller timber grid shell type structures. So there's a lesson to be learned there. The other thing really in material is that as structural engineers, we are looking at the space structure. But again, the measurements show that a lot of the carbon in our structures, in our space structures, is actually in the surrounding building, in the foundations and in the associated material. The space structure itself, we are designing, and there's lots of lectures on how we're optimizing these. But I don't believe that we're putting the same amount of effort into optimizing the other bits of the structure, and that's where a lot of the carbon is. I've been doing some research in that I'm doing a talk in 2 weeks' time for the iStructE on bridges, and I was looking at some data for predictions in the use of steel and the carbon in steel, which is a large part of what we're doing in space structures. And the net zero, there is no net zero for steel. The increased projected use and offsets any savings. And sort of currently, the best estimate is that we're going to stay roughly where we are. We're not going to get down to net zero for steel. It's a similar issue with concrete, that unless we actually drastically reduce the amount we're doing, then any savings that we get from better electricity that's not driven by coal, or smelting that's not driven by coal but by cleaner electricity, it's all lost. So for me, the message is we have to find a way of reducing the amount of materials that we're using in our structures. And I think that for me is the key message.
Thank you, David. Corentin?
Yeah, okay, sorry. Thank you very much. Yeah, so I mean, we are here, Olivia and I, as co-chair of the new working group 18 on that, and actually the working group changed its name last year, and now it's called Lifecycle Design and Assessment. And the reason why, maybe as an introduction, the reason why that change happened is because there is an understanding that the responsibility of the designers goes beyond the design itself and what is produced. So what matters is not only what is produced, but also what will come next, how the building, the structure is used, what is its end of life, and potentially what could be its future service lives, or the future service life of its components. If I hear the previous presenters, I mean, thank you very much for the presentations, Michael Kutken and David Collings. That's always inspiring. And if I summarize it quickly, I hear the first call to create new materials, and I understand materials that are that emits less greenhouse gas emissions, bio-based materials. I understand the second call as reducing the amount of materials in structures, so optimizing the system itself, and probably that there is a third way in order to decrease the environmental impact of structures, which is to expand the service life of existing structures, but also of its components. And there we entered the realm of the circular economy, circular design, and beyond the recycling of material, how can we reuse components of existing structures or bigger parts of existing structures into new ones. And so maybe that's the future materials that we have developed. Maybe they are already there in the cities that are built already. And I'm coming back to another comment, if I can have 2 more minutes. I mean, something very interesting that was said by David Collings, and we don't have the numbers, but I wouldn't be surprised neither if the shell and spatial structures worldwide only account for 1 or 2% of all greenhouse gas emissions related to the construction industry. And so we are here at the IASS, right? The International Association for Shell and Spatial Structures. So what can we do as researchers, designers of IASS? What can the IASS community do if we want to tackle this climate emergency? It was discussed. So indeed, we can improve the shell and spatial structures, but we will only address those 1, 2, maybe 5% of all greenhouse gas emissions. So it's just a drop in the ocean. It's not what is needed. We need way more than that, as was highlighted earlier. And so probably that the real challenge for us, the IASS community, is not to reduce the amount of materials, not to have new materials, it's not to extend the service life of space and spatial and shell structures, but it's really to find ways to expand the range of applications of the methods, of the tools, of the typologies that we are developing at IASS. So how can we extend the range of applications and address the needs and the constraints of these other 95% of the production of buildings and structures worldwide? And that's a real challenge. How can we really tackle their needs and their challenges, and in order to really make a change with regard to the sustainability of the construction industry? And that's, I will leave with that. Thank you very much.
Thank you. Olivia, do you have anything to add?
Yeah, well, I fully agree with with Michael, David, and Corentin. And but I think our main problem and challenge is that people ignore more or less their impact. If you speak with anybody, nobody really understood what is a kilowatt per hour, what is a kilo of CO2 emission, and people don't want to change their life with impact that they don't really understand. And I think we have a huge challenge to well-inform people to change their behavior. And I think it's a huge challenge. I also think with Corentin that reusing material or extending the expected life of a material is a really interesting and coming challenge that we have, and we need to design this way, really thinking about the end of life. And I think what we're doing at the moment is okay, we have a huge problem of climate change, but we also you have a huge problem of pollution, as it was mentioned by Michael. And I think it's important to speak about all the problems and not focusing only on carbon. And we have to accept that in the 21st century, we have to accept complexity. And when you do a life cycle analysis, you have 18 parameters that impact 18 parameters that can impact in your analysis, and I think we have to take care about all of them, and not taking only and speaking only about carbon dioxide emission or equivalent. So I think it's a great challenge of the 21st century is to accept the complexity and to develop the tools to tackle this complexity. And I think it's in this way. I think it's important to think in a way that. About the reversibility and how much a generation impact in a permanent manner to the next generation. And I think no generation has the right to destroy the environment or to destroy the climate to the next generation. And I think we have to show to everyone that what we're doing has an impact to the next generation, and doing nothing is being selfish to the next generation. And this is, I think, not acceptable. But I think our big problem is that not so many people have understood this. And I think, well, the general population have not catch the huge challenge we have.
Thank you. Just starting off with one question. I wonder if you all or a couple of you could comment on, it's clear that maybe what we used to think of as good or high profile projects or things that got awards need to kind of be, the metrics need to change. So when it comes to industry, when it comes to, and education, what do you guys want to see done in terms of things like our curriculum, where we've all take mechanics, we all take material science. Now there needs to be part of our curriculum is life cycle design, sustainability, as well as on the industry side, when we're looking at codes and things like that. What are tangible, concrete things in those two fields, since this is the community of IASS, can we do or should be done?
Am I audible? If I could mention, in terms of teaching, for me, it's incredibly important now. I see this as something of a new world that we're in, and we need to be educating in a very much broader manner. And I think if we just specifically say, okay, we will still have things called engineers, those engineers really do need to understand the context, the whole world context, far better than they do, so that they can understand the project outcomes that they're working on and steer towards better outcomes. So we can no longer really educate people into the narrow silos that we currently do educate. And that means, a better social appreciation of human beings, a better understanding of the geography of human beings. It's important for all of us. So it frustrates me that we're so siloing people at a time when we really need to understand the context, which is why I talk about, the system of systems. We need to understand the whole, as well as be experts in a part of the whole.
Well, I would concur with that in that I think my research is showing the same, really, that we can't just think about the shell and spatial structures. We need to think about the whole building if we're thinking about this, including the foundations, and that we shouldn't just be interested in the architecture or the shell. It is the whole, and if we just look at part, often we're finding that a large proportion of the carbon is slipping through our fingers. We're just not looking at it, and we must capture that sort of thing. I did want to say something about life cycle as well, in that I think I see a lot about life cycle, and particularly in bridges where we have 100-year life, and I think we just need to be careful, because this net zero problem is it's not a long-term, well, it is a long-term problem, but it's something that we need to solve quickly. And I think we do need to be careful about offsetting things such that we get some benefit in 50 to 70 years' time, when the problem needs to be solved in the next 5 to 15 years. And so therefore, to me, that raises some slightly different issues and puts a slightly different complexion on the life cycle method of analysis.
Okay, thank you. We're already out of time, but I think I'm going to still pursue one more question. So, Corentin, you had mentioned that designers have responsibility for the building post service life, beyond the use of the building. And the question is, how much power do you think designers have to actually influence that?
Yeah, a lot. And actually, I mean, Olivia already gave part of the answer, and it's and my answer, I guess, would be also a good way to answer to David's comment on life cycle. I mean, the way, you know, the designers, they design. I mean, they make a lot of choices during the design phase, and those choices also impact the end of life and the potential future reuse of the full system or of the parts. And there are well-known approaches, for instance, design for disassembly, reversible design. Those are choices that are made at the design phase already, and they will impact the end of life and the next service lives of the components. But also very simple facts. I mean, making sure that the structure can be easily maintained over time. I mean, it's not. It's stupid. It's there, but I mean, we should emphasize that as well. How can we? And then there are also other harder questions. How can we ease future reconversion of existing buildings? So we don't know what the future will be made of. We don't know the needs of future generations in terms of spaces, architectural spaces, and so on. But how can we try to allow future changes and future accommodations of future needs of the existing and newly built structures? And that's addressing the full life cycle of the structures without going into the numbers, just addressing principles. Yeah.
Okay. Last question for, if we can go around for each of you, just to try to end on an uplifting note. We have the community here. We got academics, we got industry, we got young researchers, we got senior professors. What is one tangible thing someone in this community, whether you're geared towards a student or to a professional, could we do tomorrow to start? What is one tangible thing? Even if it's open up and go read the Node Notebook, for example, or something like that. What is one tangible thing you would leave all of us with something to do?
Well, I'll step in. Yes, definitely read Kate Raworth's Donut Economics. Gives you a very broad picture of what we're talking about here. It's certainly a much bigger issue than any one of us can tackle. But I think we need to, the big thing for me is get better informed. Do not be an ostrich. Do not hide away and say, nothing to do with me. I can't do anything. We all can do something. We just don't know what it is yet. And the more informed you are, the more likely you'll find a way of fitting what you're doing, your research, your projects, into a better space. Being better informed is the first priority.
David?
Yeah, mine is very similar. I think it's just think about it. You know, whether you are a student starting, whether you're a practicing engineer or an academic, if you are thinking about net zero or carbon as well as cost and materials, then that's part of the solution. Think about it.
Okay.
Yeah, more or less the same thing, and ask yourself why. So why does it make sense with regard to the climate emergency? Everything, I mean, we can do a lot of things, we can do many things, but it's not because we can that we should make them. And so just ask yourself, why does it make sense to do that with regard to the environmental emergency for everything?
Yeah, and yeah, I fully agree with all of the speaker, but I would add to simply say, why not imposing right now to do a life cycle analysis of any construction that will be built from now, and for any students in an engineering school to be able to do or to understand clearly what is a life cycle analysis.
Okay. Michael, did you want to add?
If you're letting me, yes, following on from Olivier, yeah, I think very hard about how we can make better use of what we've already built. We've been building in countries like the UK for hundreds and hundreds of years. We've got a heck of a lot of buildings. We're using them very poorly. Think this, of course, is not necessarily for researchers, but as you move on into the active, beyond the academic world, we've got to make better use of what we've already got. We cannot carry on piling concrete into the earth and into the sky and steel into the earth and into the sky, because as David says, it ain't good enough. It's not fit for purpose. It's a carbon creating material. So we've got to make better use of what we've already got.
Okay, thank you.